If x minus r raised to the m is a factor of a polynomial f, and x minus r to the m plus 1 is not a factor of f, then r is called a real zero of multiplicity m of f. That's kind of a mouthful. Let's look at the polynomial f here and identify what we need. It's not as bad as that might sound. First, we want to recognize what the zeros are. We have three factors here. And each of those factors will generate a zero. This first one, 2x squared, if we set that equal to 0 and solve, we will get that 0 is a 0, or 0 is an x-intercept. And its multiplicity is indicated by the degree or the power there. So the multiplicity is 2. The next 0 or x-intercept will be found here. If we set this factor equal to 0 and solve, we would get that -1 is a 0 or x-intercept. Its multiplicity is indicated by the power. We don't see a power here. It's understood to be 1. So it has a multiplicity of 1. And then this factor will generate a 0, which is 3, or an x-intercept of 3. Its multiplicity is indicated by the power. Its multiplicity is 4. Multiplicity is going to tell us something about the graph. If r is a real zero of even multiplicity, then numerically what's happening is the sign of f does not change from one side to the other. What we're more interested in is the graphical part. If r has an even multiplicity, then graphically the graph is going to touch the x-axis at r and basically bounce off it. Think of x squared. At 0, the quadratic bounces off at that 0. It touches and turns around. If r is a real zero of odd multiplicity, then numerically the sign of f changes from one side to the other. But what we're more concerned about is graphically what's happening. The graph is going to cross at that x-intercept. So think of x cubed. We're somewhat familiar with x cubed. 0 is an x-intercept. And at that 0, since we have odd multiplicity, it's going to cross the x-axis. The graph actually cuts through at that 0. Whereas with even multiplicity, at 0, it bounces and turns around.